So, I got this extract from a document from US EPA from Glenn Suter. This is from 1992, and it says that what they ask for the risk managers is that you want to have, I can't really read here, so they expect a statement of confidence in the assessment, and all major sources of uncertainty, along with a statement about their influence on the conclusion. And I just want to give some context, because my talk is about how we could do a bias adjustment. I want to give a context in where that comes in. So this is part of the process of uncertainty analysis, and one can sort of simplify this process to be that we identify these sources of uncertainty. And what we're witnessing here is the sort of marriage between systematic reviews and evidence synthesis, where we have critical appraisal as an important method, with risk assessment, where we want to evaluate and make statements about risks. And the principles for systematic review are sort of entering the area of quantitative risk assessment. And now when we look at the principles of how we do uncertainty analysis, we sort of get this whole toolbox of methods from your field that we're going to work with in the context of doing assessment. So uncertainty analysis in the context of a scientific assessment, it has these steps that we identify sources of uncertainty, which could be anything that is causing limitations in the knowledge we have. And then we evaluate their combined impact on the conclusion. And we can then summarize the impact of all these limitations in knowledge in some way. And then if the conclusions are acceptable, if the level of uncertainty is low, then we can make a decision. If not, then we have to go back, we have to refine the assessment or try to reduce uncertainty somehow. So when I look at the process of identifying uncertainty, we then have uncertainties associated with inputs and methodology. And there are so many lists of different types of uncertainty, but basically it can be that we have variability or heterogeneity, we have errors in the measurements or the methods we're using. We can just have limited knowledge about the underlying processes, or we can have disagreement between experts. And then the next step to evaluate is that we take into account everything we know, data, evidence, modeling, outputs from modeling, and then we together with the source of uncertainty, we evaluate the impact. And here, I just want to put this in here, because when we do this part, since we're considering uncertainties associated to the methods as well, it requires judgment. So we can do this by an individual judgment, but usually it's the group of experts that does this judgment to make it more into a scientific process, capturing the reasonings, so we can sort of justify the conclusions made. We can also construct these rules on how to reach a conclusion from these pieces of information we have. But even if we construct these rules, we need to sort of decide what is a good rule. So judgment is included there as well. When it comes to summarizing, I often turn to research on how to think about uncertainty. And in this paper by Van den Bless and colleagues, they describe different things that we can sort of, what we are trying to express uncertainty about related to conclusion. So it could be a fact, it could be a number, or a scientific hypothesis. And this is useful to think about, because when we talk about describing uncertainty, like what are we uncertain about, sort of is important to think about. So a fact could be whether an agent is carcinogenic or not. A number could be the dose at which there is a health effect. And a scientific hypothesis is like a possible mechanism for the effect or the form of a dose relationship. And whether we are trying to summarize things about scientific hypothesis, it's not, I mean, there could be an infinite number of other scientific hypotheses. So the way we characterize uncertainty is different when it's a fact or a number. Okay. What we see here, when we look at these different areas in organizations producing scientific advice, is that there are different practices. And we can see that the communication of uncertainty occurs at two levels. Van den Bles and their colleagues, they sort of refer to this as direct and indirect uncertainty. They're not really happy about this terminology and don't get stuck in it. It's just more describing that we can express uncertainty about the conclusion, or we can express uncertainty about the knowledge which are behind the conclusion. And what we see here is that this indirect uncertainty, it's often expressed qualitatively. And this is, for example, I will show some examples soon. And then when it comes to direct uncertainty, we can choose to express this quantitatively on a meaningful scale that decision makers understand, but it can also be expressed qualitatively, what we see. So here are some examples. IPCC, they communicate uncertainty in two ways. The indirect uncertainty as a confidence and direct uncertainty as a likelihood scale. Cochrane, they have indirect uncertainty when they grade the certainty of the evidence, and then they have direct uncertainty, which are things coming out of the statistical analysis, like uncertainty range of some sort. Here is an example from the ERIC system. They're summarizing the evidence in qualitative expressions, which could be seen as indirect uncertainty, and then the evaluation is then the classification, which is then a direct uncertainty in a qualitative way. The OHAD principle, we have indirect uncertainty, this thing where we work with confidence and we upgrade and downgrade and we end up with a confidence in the body of evidence, and then that is then translated into a qualitative scale for the direct uncertainty. So the key issue here is that should one then communicate these things side by side, or should one let the indirect uncertainty be integrated in the communication of the direct uncertainty? Or should one just sort of let the indirect uncertainty guide how to communicate direct uncertainty? And what I've seen here at this conference here is that there are examples where there is integration occurring. But this integration results in a qualitative statement of the direct uncertainty. And I think that even do we communicate direct uncertainty, it's important to show the path from data and evidence to the conclusions. I'm not saying that one should not communicate all these things. It's just that, is there an integration occurring or not? And this leads to what I'm actually supposed to talk about, which is a method for integration. It's not a complete method. It's not leading to the final characterization of uncertainty in the conclusion, but it could be a helpful device on the way. And so this is then options to consider risk of biases in individual streams can be to remove studies with high risk of bias, or to evaluate using sensitivity analysis by including or excluding them, or we can include them but adjust for bias. And quantitative bias modeling or bias-adjusted meta-analysis, it has many names. It is a method that has been around for a long time. And it is, I haven't seen anyone used it, or there was a mention of it earlier today. And I think that why aren't we doing this more often? Maybe it's difficult. But if we allow ourselves to work on this more complex quantitative evidence synthesis modeling, we can actually start pooling or integrating streams of evidence which are of different types. And I will just show you a suggestion I have where we can sort of take the information from the risk of bias assessments on individual streams, include them in these quantitative evidence synthesis, and then create quality weights from the risk of biases to make adjustments. And the reason I want to link it to the risk of bias table is that this could then be turned into a sort of semi-automatic way of doing this. So one don't have to, I mean, this information from the risk of biases, it's really, really useful. So how can we use this in bias adjustments? So let me start with an example which is taken from a paper by Spiegelhalter and Best from 2003, where they wanted to do an evidence synthesis to compare revision rates for two methods for hip replacement. So they have 3 streams here. One is registry data, another one is randomized controlled trials, and the third one is case series. So these are quite different. Can we really include them into the same quantitative analysis? Well, here we put up they have this table in the graph, and you can see that if we run the analysis for each of these studies differently, we end up with quite different results, where the randomized controlled trial says that there is basically no difference between these two, and the registry and case theory says there is a favor of the Stanmore processes. But they also do this, they discuss then, so the randomized controlled trial, it's something which has higher quality or a lower risk of bias compared to the other studies. They create these quality weights, they call them, which is it's an assumption about how the variability between these different streams, how they relate to the internal error, the bias within each stream. So basically, if you have a quality weight of 1, it means that you don't have any bias, internal error. And if you have a quality weight closer to 0, it means that your bias is huge. And now I'm talking about bias not as a systematic error, but more as a random error. But the consequences of including this is that it sort of gives lower weight to that stream in this evidence synthesis by basically flattening the likelihood from that study. So they run this adjustment, a model with 3 different values or set of values on these quality weights, and then they end up with different results. So what we see here is that we have the 3 studies. We then get an unbiased effect. And the question is here, can we then turn this information about the relationship between these different studies in an automatic way and do this setting of the quality weights in an automatic way? So what we came up with was that a way to do this, first, of course, we need a statistical model, so we can formulate a hierarchical model which allows for expressions of these 2 errors. We implement this in a Bayesian framework. And then we make some judgments about for example, the magnitude of heterogeneity, so we can put a prior distribution on this between study error. And we can also make judgments or assign assumptions about these bias factors. But these bias factors, that's really challenging. How can you know these values? Well, you don't. But what we can say is that we can say something about the relation between them. So the randomized controlled trial should have the highest weight, and the case series should have the lowest weight. So we put up this order. We can then assign a maximum and lowest value on these quality weights. And what we get here to the right here is then a polyhedron, like the possible values under which we want to do this analysis. And here is where the probability-bound approach comes in. So I'm not running one model, I'm running all possible models within these constraints, and then I'm optimizing, searching for the lowest possible value on, let's say, the uncertainty range and on the expected value, and then I can see, in a quick way, summarize what the consequences are of this bias adjustment. And what we did then is that we added another overall estimate of the effect, which is the bias-adjusted effect. And here we can see that the expected value in the middle has a lower and upper bound because we are optimizing under sets of models. And we can also see that we get the lower bound for the lower probability bound, and we get a higher value for the upper probability bound. And we can also see under which combinations of quality weights that we get these bounds. So what we did then was that we tried this on an evidence synthesis done by Cochrane. And this is a study that was published by my PhD student, Yvette Ruiz-Cruz. So from this evidence synthesis, we had a risk of bias table. So what we did was that we took all these domains, and we can see here, for example, that the first and second domain, they have unknown risk of bias, and the third one has, 2 of them has a low risk of bias, and 2 of them are unknown. And based on this information, we created, for each domain, we created this polyhedron, making assumptions. And then we ran the bias-adjusted meta-analysis, and we summarized the overall effect, taking into account these biases. So this is a way to sort of link the different domains into what consequences it might have when we do the adjustment. And we can then also take into account all the different domains by using the summary of it, and then we can compare it to the unbiased estimate. And this is the method that we propose, that one could try and see if it's possible to make this work for, as a general thing. The only thing you need to do is to set up a model and make judgments about the lower and upper values on the quality weights. And one can also add systematic biases, but that is a little bit more, it requires judgment coming out from the risk of bias evaluations, maybe on the direction of the bias. So to conclude, I want to say that bias modeling, it makes it possible to actually do this integration of indirect uncertainty into expressions of direct uncertainty in a quantitative way. It requires a statistical model, and it requires judgments on variance and bias factors. And I have presented a way to do this using information from the risk of bias table. And then I welcome any comments and suggestions on how to implement this further. Thank you so much.